Hello guys, welcome back to lecture series on discrete mathematics. So in our today's videos guys, I'm gonna explain to you all a symmetric closure. In my last lecture, I explained here a reflexive closure, okay, reflexive, symmetric and transitive closure. I'm taking these three as a three different lecture so that you can understand the concept easily, okay. So let's start symmetric closure, okay. Yes, always remember that guys, whenever our sets do not hold reflexivity property, so in such a case, to make in order to make that set as a reflexive, we should have to operate some properties, okay. So for that we call the reflexive closure. Similarly for the symmetric, our set is not symmetric, but in order to make it symmetric, we have to apply some property called as a symmetric closure. And similarly for the transitive closure, our set is not transitive, but in order to make it transitive, so we have to apply some other properties, so we call it as a transitive closure, okay. So this is the straightforward meaning for these three sentences, okay. Yes. And plus anti-symmetric, most of the students don't know the meaning of anti-symmetric. Let me explain here. Anti-symmetrics, anti-symmetric, okay. Symmetric property, what it says that for the we need at least two elements to show the symmetricity, okay. Yes. So when A related to B, this implies B related to A, so then we call it as the symmetric, okay. This is a symmetric property, okay. But anti-symmetric, it says that we have to add one more proper condition: A should be B, A should and B should be equal, okay. So that means this is the anti-symmetric, okay. This one is the anti-symmetric, okay. So this is the actual meaning of anti-symmetric, okay. Symmetric means A related to B, B related to A, and not symmetric means A related to B but B do not relate A, okay, or A do not relate to B, okay. So in this case we write not symmetric. Anti-symmetric means both are related but both should be equal, okay. So obviously that can hold the symmetric property, okay. So that we call as, in special case we call it as the anti-symmetric property, okay. So let's start a symmetric closure for today's lecture, okay. So I hope you all have understood why we are applying symmetric closure, because whenever say do not hold a symmetric property, okay, so in such a case we apply symmetric closure, okay. Yes, right. First what we have, R is the relation on a set U, okay. R is a relation on a set A. We are having set A and which is R is a relation on a set A, and which not symmetric, okay, which is not symmetric, okay. R is a relation on a set A, but R is not symmetric, okay. Now what we do in such a case, we define new relation again, like a reflexivity property, okay. We define new relation here, set P, okay. I'm defining new relation here, okay. Okay, I'm defining new relation here. Consider that P as R union, consider that R inverse, okay. R union R inverse, okay. So this one called as symmetric closure. This one is called as symmetric closure, okay. This one is called as the symmetric closure, okay. Only if R union R inverse is a symmetric relation containing R, okay. So I'm not adding more data here, so directly we go to the example, okay. So R inverse, let me take the R inverse, okay. What is the actually R inverse? R inverse is the inverse of R, okay. So let me tell you in the form of order pair how the inverse can be written, okay. So if AB is the order pair, then its inverse, AB is the order pair, then its inverse we write BA, okay. This one is the inverse for AB, okay. So you can take for any other element, okay. CD has inverse DC, okay. So what about for A? This is like identity element, we write this inverse as only A A. Okay, so this is the inverse for element. Okay, let me define some of the example, guys, so that I want to make this video shorter. Okay, not that bigger. Okay, example, I'm taking set A as a only 3 element, not bigger one. Okay, A, B, C. Okay, I'm taking A as a ABC, and the relation R, which is not symmetric, we want not symmetric. Okay, so you can take A related to A. Okay, uh, and then we can take B, A, order pair B A. Okay, A and B A. So this one is R is the relation. Okay, so you can observe our set here. R is not symmetric. Why R is not symmetric? Because A related to A is there, it doesn't mean anything. Okay, but B related to A, when B related to A is here, this implies we want A related to B also. But order pair AB is not there, na? Where is A order pair AB? Not, it is not present here. Okay, so this implies not symmetric. This implies our relation is not symmetric. Okay, so we have to define R inverse. Okay, inverse of R such that this R set can be symmetric. Okay, so what is the absent term here? R inverse, we write single term order pair AB, so that R can be symmetric. Okay, yes, and we are taking their union. Okay, I'm defining new set P here, that is R union R inverse. Okay, so AA BA, R union AA, then BA, this is our set R. Okay, this is a set R, we are taking union with the A inverse AB. Okay, A, B, A and AB. Now see that we can see that B is related to A, then A is related to B, A is related to A, then A is related to A. That means our relation R, it holds symmetric property. So then we call as this set P as a symmetric closure. Okay, I hope you all have understood, guys. Okay, it is very easy symmetric closure for understanding. Okay, that means we have to add a minimum number of order pairs so that our set can be symmetric. Okay, so if you want, you can note it down these points. They are going to be very important for our today's lecture and for your exam, guys. Okay, I hope you all have understood the meaning of symmetric closure. Even after, if you found anything difficulty, guys, confusing, difficult, let me know in my comment section. I will come up with a similar videos. So that's it for our today's lecture. So thank you everyone, thank you for my today's lecture. In our next lecture, guys, I'm gonna go for transitive closure, which is very important. Okay, so that's it for today's lecture. See you in our next lecture.